Hi, this is Shrishpam Krishna and this is my project summary video for LVJUSD's Science Odyssey 2022. My project this year is StackerBot, using robotics and artificial intelligence to stack shoes into shoe racks. Before we get started, let me give you some background information. In today's world, we humans are a busy species, focused on improving our lives and furthering our society. Yet, we are still bogged down with menial tasks like vacuuming our floors, cleaning our dishes, washing our clothes, and putting away our shoes into shoe racks. These chores are necessary to keep our houses running and our mental state calm, but still feel so redundant. I strongly believe that we can use the technology available to us to automate and help us with these tasks. Some progress has already been made in this field, but so much more is needed for a future where humans can focus on what is important in their lives. This year, I have dedicated my project to solving one of these chores, the annoying and cumbersome cleaning up of the shoes scattered around almost everyone's shoe racks. This might seem simple at first, but from personal experience, this is extremely hard to execute efficiently from an engineering standpoint. Let's get started. First, I want to talk about my engineering problem, my engineering goal, and my engineering outcome. The problem I aim to solve in this project is the menial chore of cleaning up shoes into shoe racks. The goal for this project is to use robotics and artificial intelligence to make the task of cleaning up shoes into shoe racks easier for humans. The expected outcome of this project is a robot with artificial intelligence capabilities that will be able to identify, pick up, and stack shoes into a shoe rack. Here's a materials list for my project. Without any further ado, let's meet the robot. Let's start with the chassis. You may notice these mechanism wheels, which are good for holonomic drive. These wheels give the robot the ability to move in all directions and rotate independently. The holonomic drive also offers greater precision and control during autonomous drive for the robot. After some research and testing, I chose a square show you there, a square layout for my chassis because that offered good stability and worked well with the mechanism wheels. Now let's look at the linear slide. It has a receded length of 306 millimeters and can reach a travel vertical of 376 millimeters, which means fully extended, the cascading linear slide can reach 682 millimeters in length. I use this slide to get my shoes to higher shelves when needed. Attached to the slide is a bar lift, and my gripper is attached at the end here. The gripper grips the shoe and the bar lift can move it away from the robot and make up for lost height from needing the gripper to be so low to grip the shoes from the ground. You may have noticed this camera here. This is for my machine learning models, which is coming up soon in the video. Now let's move on to the electronics of this robot. I have 5 motors, the wheels and the linear slide, and they're controlled by 3 motor controllers. 1 motor controller for the linear slide, 1 motor controller for the back wheels, and 1 motor controller for the front wheels. The RoboClaws, which are the type of motor controllers I use, they're connected to the Raspberry Pi through the breadboard that you see here. I also have 4 servos on this robot, all connected to the servo hat, which is directly connected to the GPIO pins on my Raspberry Pi. These servos control the bar lift, 2 of them control the bar lift, 1 controls the gripper, and 1 controls the rotation of the camera. You might ask why I did not solder some of this setup, or more generally, why I didn't make this more permanent. That's because I decided this type of setup would be best because I wanted a flexible and easy to access system for all my electronics during building and testing. Now you may be wondering, how is all of this powered? Well, the Raspberry Pi is powered by this Anchor power bank, and my 3 RoboClaws and my servo hat are powered by the 12-volt battery in this bottom pink container. That's the overview of this robot. Now let's head over to an RC controlled demo. Hey guys, I'm now going to be doing a demo of the robot using RC control to pick up the 6 shoes behind me and stack them onto this shoe rack right here. Let's get started. And now, StackerBot here has finished stacking these shoes onto the shelf. Let me show you the finished product. What started as a messy bunch of shoes has now become a clean and organized shoe rack. There you guys go. And that was fully RC control. I did not touch these shoes in any way. Now that you've seen the robot stack shoes into shoe racks with RC control, let's move on to the real deal of this project, automating that process. My goal for this project was to use robotics and artificial intelligence to stack shoes into shoe racks. This would free up a menial chore that humans are subjected to so they can go focus on more important things in their life. Me personally, and I'm sure quite a few of you would agree, like this robot RC control mode because it makes a once menial and annoying task into a fun and gamified experience. But alas, that is not the goal of this project. So, let's talk autonomous. To automate this project, I first needed to enable the robot to see its surroundings. I did this with a Logitech webcam that you saw previously. The robot would use this setup to detect objects, in this case, shoes. Coding-wise, I have used OpenCV for image processing and Edge Impulse to build models for the Raspberry Pi. Edge Impulse makes it easy to build object detection and object classification models for single-board computers like the Raspberry Pi. Now, let me take you through the process of how I built my models on Edge Impulse. Let's start our tour in the data acquisition phase. Here, I took lots of pictures and went through each one meticulously to box where the shoe was in each picture. Now, let's go to the Create Impulse section. This is where I configure the pre-processing steps of my model. Now let's see how my model trained. I trained this model again a few minutes back, and it had a 96.8% accuracy. Now let's see how well this model does in testing. Let's click Classify All, and another 100%. Nice. Now let's go to Deployment. After I made this model, I used Edge Impulse to download the model onto my Raspberry Pi so I can call it in my code. In this clip, you will see how the robot interacts with the model to scan its environment, detect a shoe, and autonomously navigate towards it. On screen, you will also see the laptop showing the camera view from the robot. This is being streamed from the Raspberry Pi using a Python Flask application. You will also see the camera on the robot scanning up and down to look for the shoe. This is due to the servo that the camera is attached to. The journey of building this robot had a lot of bumps. I have listed some of these challenges on this slide, and I'm going to talk about two specific incidents that had large impacts on my project. First, I spent $450 in total on the 3 motor controllers for this project, but when they arrived, I discovered that I needed a Windows machine to configure them. This was a problem because I did not have any access to any usable Windows machines. I first tried setting up a virtual Windows machine on my Mac, but that was very laggy. So I revived an almost broken and very old Windows machine to configure my motor controllers for the project. This consumed a lot of time and energy, which I could have instead put towards building my project. Another major setback was when the mini monitor that was attached to my Raspberry Pi broke today. I was using this mini monitor to view the camera feed of the robot. I purchased this monitor for $90. So, as an alternative, I had to set up a Python Flask application to stream the camera feed on the network, so I can view it from another device connected to the network. This caused major disruption to my schedule to film this video. My 4 main constraints in this project were time, money, lack of resources, and limited expertise on subject matter. In conclusion, at the end of this project, I've built a robot with artificial intelligence capabilities that can stack shoes into shoe racks. This fulfills my engineering outcome. This combination of AI and robotics has also opened up a huge world of possibilities and ideas that I plan to explore in my upcoming projects. My passion lies in bringing artificial intelligence into the world of robotics to help humans. Due to the constraints in my project, the autonomous functionality of my robot is still jittery and not resilient. I would like to invest in a better microprocessor like the Jetson Nano, which is specifically meant to build artificial intelligence projects. Also, even though Edge Impulse let me build my machine learning models in a quick amount of time with limited knowledge on machine learning, it also had its own limitations on the size of models that can be built for free. I plan on expanding my knowledge in deep learning and image processing and build my own custom models to make this autonomous drive smooth, seamless, reliable, and resilient.